Okay, in this lesson we're going to look at a few examples where we're going to deal with problems initially with the norm reaction and then with a few problems with friction involved. Remember we said the amount of friction an object can offer really depends on two quantities. We said the first quantity was the mass of the object and the second quantity was something called the coefficient of friction. Okay, mu. And mu is, it's a ratio, it's a fraction. It's always between 0 and 1, which is something, worth remembering. So 0 is always less than or equal to mu, which is always less than or equal to 1. So mu, the coefficient of friction, and mass. Okay, and the coefficient of friction depends on, what kind of materials, I suppose, are involved. The mass of the object is going to affect the normal reaction. We also said that maximum friction, the most friction that an object can call upon, is equal to mu times the normal reaction. So those are things we're going to think about going forward. A couple of things about normal reaction first. Let's just look at an example. It says a desk of mass 10 kilograms stands on the floor. Calculate the normal reaction between the desk and the floor. There's my desk, this is my force diagram. What forces are acting on it? Well, the force acting on the object by gravity is called the weight of the object, which is always equal to the mass of the object multiplied by little g. In this case, the mass of the object is 10 little g, 10 times little g newtons. Okay, and that's pretty much about 98 newtons, taking g to be 9.8. Okay, that's what's acting downwards. The desk is standing on the floor. One thing to note, if it's standing on the floor, it is not accelerating downwards and it is not accelerating upwards. That means there's no net force in the vertical sense, which means the upward forces must equal to the downward forces. The desk is standing on the floor, the desk is pushing on the floor is pushing back on the desk. That push on the desk by the floor is called a normal reaction, and that has to be equal to 98 newtons. Why? Well, because if it was less than 98 newtons, the desk would be accelerating downwards through the floor. If it was greater than 98 newtons, well, the desk would be accelerating upwards into the sky, so it must be equal to 98 newtons, which means there's no net force acting on this object, or the net force is 0. This object is not going to accelerate downwards or upwards. The normal reaction is 98 newtons. A man of 72 kilos stands on the 10 kilogram desk. Okay. Calculate the normal reaction between the desk and the floor. Again, we're looking at force diagrams. I'm just looking at the force diagram for the desk here. So what forces are acting on the desk? Well, just like before, the force of gravity acting on the desk. The force of gravity on an object, it's called its weight. We said the weight of the 10 kilogram desk would be 98 newtons. So we've got a 98 newton force pushing down there on the desk. Also pushing down on the desk is the force of the man on the desk. Okay, so the man is pushing down. The weight of the man is pushing down on the desk as well. And so we've got the weight of the man, the force on the desk by the man. And that's going to be whatever the weight of the man is. It's going to be 72 times g. 72 times g. Which is about 705.6 newtons. So those two forces are pushing down on the desk. Again, assuming the desk is just standing on the ground and is not kind of sinking into it. The desk is pushing on the ground, which means the ground is pushing back on the desk. And the desk is not accelerating downwards, nor is it accelerating upwards, which means this upward force, this normal reaction here, will be the combination of these two values. So 803.6 newtons. Okay, so the normal reaction in this case is greatly increased. Why? Well, because the man has stood on the desk, and that increases the push downwards on the desk. There's two downward forces on the desk, and the normal reaction is the only upward force in the desk, so that has grown. Here's a force diagram all done out, and it says the mass of some object is 500 kilograms. It says the coefficient of friction is 1/10. We're going to have the weight of this object pushing downwards. We're going to have some normal reaction pushing upwards. Because there's a coefficient of friction, we've got some, maybe it's a tension pulling this thing to the right over here. So we're going to have some friction force pulling out to the left. So we go through each of these things. Remember that friction is defined as being the coefficient of friction multiplied by the normal reaction. That's, I should say, the maximum friction. That's the most friction that can be called upon. Okay? The friction will never be greater than the force, it's resisting. It can't be, because that would mean friction would create motion, which is not possible. Friction only opposes motion. Doesn't actually create motion. So what we have on this object, again, this is just a force diagram. We've got some object here. We have the weight of the object, which is the force exerted on the object by gravity, which is always the mass of the object multiplied by little g. In this case, the mass is 500. Little g is, what do we say, 9.8. So this is going to be about 490 newtons. So the weight of this object is 490 newtons. Assuming, assuming this is traveling horizontally, let's just say, assuming horizontal motion. So if I assume this object is traveling horizontally, which of course I shouldn't unless I'm told, but I'm going to in this case, well then the normal reaction here, if this is something sitting on the ground, the upward force would also be 490 newtons. If it wasn't, if it was less than 490, this object would be accelerating downwards. If it was greater than 490, this object would be accelerating upwards. Okay, the maximum amount of friction this object can call upon is going to be 1/10 of 490. It's mu times r. Maximum value for friction is mu times r. So it's 1/10 of 490. That's 49 newtons. That's the most friction it can call upon. Of course, it wouldn't call upon anything more than the pulling force here. So it's going to call on all of its 49 newtons in this case. Okay, remember F net equals MA. The net force in this case would be the 100 Newton pulling force minus the 49 Newton friction force. So we'd have a net force of 51 newtons, and that would equal to the mass of the object, 500 times the acceleration. So we can work out that the acceleration of the object will be 51 divided by 500 meters per second squared. Okay, let's look at one more example. And this is kind of a word question. It says I push horizontally on a 50 kilogram desk with a force of 300 newtons. Given a coefficient of friction of 0.6, find the acceleration of the desk. So we have a desk. I'm pushing horizontally on it. A desk, we can assume it's sitting on the ground. I'm pushing horizontally on the desk with a force of 300 Newton. That's kind of the propulsive force, that's what's pushing it forward. But also with the desk we have other things happening here. We also have the weight of the desk. If it's on the ground, there's going to be some kind of normal reaction. And also pulling to the left here, there's going to be some friction if I'm trying to pull to the right. the weight of any object is equal to its mass multiplied by little g. This is a 50 kilogram desk, so this will be 50 times g. Okay, 50g, or 50 times 9.8, which will be, I think, 490 newtons. A desk sliding across a horizontal ground, well, the normal reaction would have to be 490 newtons also. If it wasn't, it would either be sinking downwards, accelerating downwards, or accelerating upwards. I'm pushing horizontally on a desk. We can assume maybe it's on horizontal ground as well. There is a friction force in here, and the most friction that can be called upon. Again, bear in mind that objects don't always call upon all their friction. They only need to call upon as much as is necessary to defeat, or to match, I should say, the pulling force. So the maximum friction I can call upon is always going to be mu, the normal reaction, the coefficient of friction multiplied by or, the normal reaction. So the coefficient of friction is given here at 0.6. The normal reaction is 490. So the most friction that I can call upon is 294 newtons. There's a pulling force of 300 newtons, so all of that 294 newton friction force is going to be called upon here to resist this motion. It's not going to be able to stop it moving, but it can certainly reduce the rate at which it accelerates. There's my force diagram, all my key details in there. My force equation, remember, the net force is always equal to the mass times the acceleration. The net force in this case, again, I'm going to assume a right positive system. 300 positive force, my 294 is a negative force, so my net force is going to be equal to 6 newtons. The mass of the object is 50 kilograms, and then we're trying to work out what the acceleration is. So the acceleration is going to be 6 divided by 50, which will be 12 over 100, or 0.12 meters per second squared. So this object will accelerate at 0.12 meters per second squared. Okay? Normal reaction is a contact force always perpendicular to the surface of, whatever plane we're in contact with. Friction force, the most friction force that we can conjure up is mu times or. And we only use that, all of the friction force, if it's necessary. If I was pulling to the right here with a force of 200 newtons, well then there wouldn't be a friction of 294 resisting me. They would only need 200 newtons to stop me moving this object. So if I pulled with 200 newtons, the friction force would also be 200 newtons, in this case resisting motion. Okay, practice, practice, practice.